Okay, we're going to go ahead and get started. So welcome to Solubility Part 2. Um, so we're going to look with a slightly deeper dive into the solubility of lead in water. And the most important moment here is that lead is not very soluble in water under typical conditions. However, there are certain lead compounds, especially some lead salts, that can be soluble and become aqueous ions. And so the solubility of lead in water is going to be influenced by factors like pH, alkalinity, and certainly the presence of other ions. So the visual that you see here is an example of the chemistry that occurs in just about all of the lead pipes that are used for plumbing groundwater into homes in the United States. And the map is actually from an article that was published where they looked at the solubility potential of untreated groundwater. And so most groundwater is accessed via a well, and then that well um, water is either treated or untreated and then plumbed into homes. And so today we're going to take a look at the solubility of lead specifically and do a slightly deeper dive. So as you can see from this box plot, lead metal is soluble in nearly all natural occurring water, so somewhere with a range of pH 6 to 8. So water that's in contact with lead plumbing can acquire elevated levels of dissolved lead. Now there are a variety of different types of ions that can co-occur with lead, which is why we have a fairly wide range. And interesting, there's different sides of the pipe in terms of contact. So this is a good example of some of the range and variation that is common to see in terms of lead ions that co-occur with other types of ions. But I show you this just so that we have a ground reference point of just how much variation there can be. So let's talk about some of the factors that actually influence the solubility of lead in water. The first problem we're going to look at builds on our knowledge from the last session that we had where we were calculating KSP values. So in this case, we're given a KSP value for lead iodide, and that value is 1.4 times 10 to the negative eighth. And then together we're going to calculate the molar solubility of lead iodide. So our first step is going to be to write out our equation for the ionization or the solubilization of lead iodide. So if this was a solid and we were to put it into water, the ions that it would form are going to be lead 2 plus, which is an aqueous ion, and I minus, which is also an aqueous ion. And the most important here is, for every 1 PbI2, we have 2 I minus and 1 Pb. So we're going to use this information, and we're going to actually use an ice table to help us make sense of this, because I got an email from someone who's like, well, how do you know whether the number that's inside the parentheses in the KSP statement is 1 or 2? So an ice table stands for initial, change, and equilibrium. In this case, we're not given information about the initial amount of our lead iodide, but that's okay because, excuse me, we know that our lead and our iodide initially are going to be 0 because we're starting out with a salt. And we know that for every 1 lead iodide, we're going to form 1 S. And for every lead iodide, we're going to form 2 I minuses. So that's going to be our change. And so that means that this is going to be 1S and this is going to be 2S. And so that's the information that we use from a mole standpoint, even though we don't actually have a number here to write out our KSP statement. So KSP in this case is going to be equal to the concentration, that's what the square bracket means, of our lead, 2 plus, and our iodide. And again, because that's a coefficient of 2, The coefficients become our exponents, so that's going to be squared. So I can rewrite this then in terms of our ice table that we just set up. So it's going to be S times 2S squared. And so that means then I'm squaring both the S and the 2. So 2 squared is 4. So this becomes 4. And then S to the 1 times S to the 2 is S cubed. And now all we have to do is solve. So we're going to input our value. So 1.4 times 10 to the negative 8 is equal to 4s cubed. We're going to divide both sides by 4. And then we're left with 3.5 times 10 to the negative 8 divided by 4. And that's going to be equal to s cubed. And if you recall, the way we resolve exponents is we multiply by the reciprocal, so 1 over 3. But we have to do that to both sides. 1 over 3. Or taking the cube root, you can do that in your calculator as well. The last thing that we do then is solve for our s, which in this case is 1.52 times 10 to the negative 3. And this is molar solubility, so it's always going to be in capital M or moles per liter. Now let's think about this in terms of our sig figs. The information that we're given was 2 sig figs. Right now our answer is 3, so we're going to make that just 1.5 times 10 to the negative third, capital M. And that's the molar solubility of lead. Now let's think about that for a minute in terms of actual numbers. So 1.5 times 10 to the negative 3 is the same thing as 0.0015, and that's moles per liter. So if I were to draw a picture, what does that actually look like? Well, 0.0015 moles of lead. The molar mass of a lead ion is 207.2. So if I were to multiply my moles to figure out the amount in grams, so that would be 0.0015 times 207.2. So that's 0.311 grams. So if I had a liter, so that's 1 liter, I would have 0.311 grams, or in this case, right, because we have 2 sig figs, just 31 grams in 1 liter. And that would be the most lead that I could solubilize in 1 liter of water. So one of the things that I want us to think about is the KSP value actually has meaning. It allows us to calculate the molar solubility of lead iodide. And based on that molar solubility, we can determine the amount in moles or grams of lead that's soluble in a liter of water. So we're going to take that information now, and we're going to go a little bit further. Because, right, let's say it's a different counter ion. So in this case, instead of lead iodide, we're going to think about the solubility product constant for lead chloride. And now we're going to be specific about the volume. So if we have a 50 milliliter saturated solution, remember that's as much lead as we can possibly fit into water, and it was found to contain 0.2207 grams of lead chloride. So now we're going to do a calculation where we figure out, right, what's the solubility product constant, or what's our KSP, based on that. So again, we're using a similar process, but they're asking for different information. So we're still going to start with the same process, though. Our process is we're going to write out our lead chloride, so PbCl2. That's a solid. Goes into, and again, we're forming our lead ion. In this case, it's always going to be Pb2+. That's the aqueous ion. And in this case, our chloride ion, Cl-. And remember, we have a 2 in front. It's also aqueous. Okay, so delightful news for us is that our ice table is going to look the same, but we have to do a calculation. So notice how they gave us the 0.2207 and they gave us 50 milliliters. So we're going to calculate the amount in terms of molarity for this process. So we're going to count moles first. So 0.2207, and that's in grams. So we're going to need to calculate or look up the molar mass of lead chloride. So in this case, the lead chloride molar mass that I have is 278.1. That's going to be in grams per mole. Now, in this case, they also give us some information about our volume. So we have 50 milliliters. Now, usually our molarity is represented in moles per liter, so we need to convert that from milliliters, 1,000 milliliters, to 1 liter. And when I do that, I get 0.0159, and that's a capital M of my PbCl2. Okay, so that's my amount in moles per liter. So I'm gonna do an ice table again. This is how I'm making sense of my initial concentration, the change of concentration, and then what I have at equilibrium. So in this case, I have all solid. I don't know what this number is, but I can assume that at the beginning, all of it is PbCl2 as a solid, none of it is Pb2+, and none of it is 2Cl. I just calculated, right, what the amount is at equilibrium, right? So they said it's 0.0159, which means that I'm adding 0.0159. Now I'm going to take this number and multiply it by 2, which is how I know that I have 0.0318. And then obviously here, right, I'm subtracting my 0.0159. And while it was all solid, now it's going to be less solid. But I don't really care about this number because I don't have the amount that we started with. But that's okay. I'm going to use what I created here. These two values are going to be what goes into my KSP expression. So my KSP expression based on the solubility of my ions is going to be Pb 2 plus, and then Cl minus squared. So if I plug in the values that I have, it's going to be 0.0159. And again, if you want, you can write to the 1 power, but you typically don't have to. It's just assumed that it's to the first if you don't have anything else written. And then 0.0318 to the second. And then when I do that calculation, double check in my calculator, I get 1.61 times 10 to the negative 5. Does anyone else get that value when they do this calculation? It's always helpful to double check.
I was still working on it. Yeah, I got that.
Sweet. Awesome. Okay, so we've got 3 sig figs, so it's appropriate. Notice that KSP does not have a unit. It's unitless. So we don't have a unit associated with our KSP, but that's our final answer. So notice we used a very similar process. So we used the ice table to be able to figure out what the amount in moles would be, or the concentration, if you want to think about it that way, if we're assuming the volume. Would be for this. So we can figure out then the amount or the calculation that we're going to do based on the information given in the problem in terms of a calculation for molarity and concentration, and then using that in combination with an ice table. So this is an example of a slightly more complex calculation associated with KSP, but it still uses information just like we did in earlier, simpler problems. Okay, one of the most important caveats when we're thinking about solubility is temperature. So now we're going to do a calculation that is specific to, in this case, lead fluoride. Again, a different ion or salt associated with lead. But this time we're going to think about a weight by volume calculation. So if you think about it, the weight of our lead fluoride relative to the volume of our water. So what does that actually mean? Let's take a moment and unpack that statement. So we're given this information. We're going to figure out what that means. So weight by volume means that I have 0.0510 grams of lead fluoride. So that's PbF2. And this percent, right, or by volume, means that it's in 100 milliliters of solution. Right? In this case, it's going to be water. So we're going to do a couple of calculations. The first calculation that we're going to do, of course, is to convert our mass in grams into moles. The way we're going to do that is by calculating or looking up the molar mass of lead fluoride, which in this case is going to be 245.196. And that's going to be grams per 1 mole. And in this case, that's PbF2. Okay, so we're going to figure out the amount that we have in terms of moles. That's 2.08. Times 10 to the negative fourth. And that's moles. Now, in this case, we're not really done because we do actually have to calculate molarity. So because this is 100 milliliters, that's also the same thing as saying 0.1 liters. If you want to, you can go through the process of showing that conversion. You could also say, for example, if you wanted to, if you needed to do this in molality, convert it to grams using the density. But for our purposes today, we're just going to do the shortcut and say that we know that 100 milliliters is the same thing as 0.1 liters. And that's going to give us a molarity of 2.08 times 10 to the negative third. And I'm going to use capital M for my molarity. Okay, so now we're going to take, right, all of this information. We have a molarity. And now we're going to think about our beautiful ice table. So we have our PbF2, which is a solid, which is going to ionize to form Pb 2 plus, which is an aqueous ion, and 2 F minus, which is an aqueous ion. And then we're going to think about our ice table. And again, we're in a space where they're giving us solubility, right? So the value that we just calculated is this, 2.08 times 10 to the negative third. And the value is this number times 2, so 4.16 times 10 to the negative 3. And again, if you have difficulty and you're like, oh, shoot, I don't remember. Remember, we always start with 0 for our ions, and this is all solid. We're going to lose 2.08 from our lead iodide because we are forming that same amount here. So this is going to be a plus 2.08. And I show this because I think sometimes, right, we can set this up if we understand the process, but sometimes it's also really nice to step back and show the entire rationale. Like, here's the reasoning behind why we can do this, so that it's not quite as procedural and it does, in fact, reflect your understanding of what solubility really means. Okay, so we have this beautiful ice table that we just set up. That's going to be what helps us set up our KSP expression. So KSP in this case is going to equal 2.08 times 10 to the negative third. And that's to the first power, although we don't write it. And then we have 4.16 times 10 to the negative third, but that has to be squared. And when I enter that into my calculator, I get 3.60 times 10 to the negative 8. So if we want to double check, can someone confirm that they too got 3.60 times 10 to the negative 8th when they entered that into their calculator?
I
I
did.
got the same.
Whee! Thank you. You all rock. You have no idea the like deep breath of exhalation that happens when someone confirms that your calculations are correct. All right, so a couple of key pieces here. Notice this is weight by volume. They could have given you weight by weight, and it would have been a similar type of calculation. Um, Notice, right, as we look at the solubility, it's still really low, right? So lead is, right, 0.00208. So if we wanted to figure out what that amount would be in grams, we could do so based on the molar mass of lead, but it's still a relatively small amount of lead that's soluble in water. Now, here's the question that we're going to ponder and do some sense making of together. Just because it can dissolve in water doesn't mean that that amount in water is actually safe for humans. So when we think about solubility, it's the maximum amount of something that will dissolve in a given amount of solvent. And we know that it's going to be a characteristic property. So lead is going to have a specific solute solvent combination, right? And different substances are going to have different solubilities relative to what they're paired with and to the local environment. When we say that something is insoluble, that means that it is not able to go into solution. Now, you'll see in some textbooks they'll use the term slightly soluble. That means with enough heat, you can get a little bit of that solute to go into solution, but typically they're not particularly soluble. And then the last piece is we have talked about how it's the composition of both solute and solvent, and that's going to really depend in some cases on pH. We've also talked about the presence of other dissolved substances. We're going to look at the common ion effect on Thursday. And then we've also thought about temperature and its influence on solubility, but you could also use pressure as well. So we're going to think about these interactions now, but we're going to actually use a different method of concentration calculation. So the expression of 1 ppm means that a solute exists at a concentration of 1 part per million parts of the solution. So there's two ways you can really think about what 1 ppm means. So you can think of it as 1/millionth of a gram per gram of sample solution, or you can think of it as 1 gram of solute per million grams of sample solution. Now, here's why I want you to take a moment and decide which of these ways of thinking about this is the best fit for you. Oftentimes, when we're creating a concept map or we're creating connections between ideas, if you have a new problem, a new scenario, a new context, that can make solving a challenge if you don't have a reference. And so having a reference for ppm of, oh, that's 1 gram per million grams of sample solution is a really great reference point. And if you have that, then you can go about solving for any number of problems that ask you about ppm. So let me show you an example of how you can think about it. So symptoms of lead poisoning become apparent after a person has accumulated more than 20 milligrams in the body. So we're going to express this amount as parts per million for an 80 kilogram person. So again, we're talking about the amount that someone can have when they start to feel negative effects. So we've got 20 milligrams, and it's useful, right, for us to convert this to a common reference point. So while milligrams is probably appropriate for the amount that's there, I need to convert this to grams for comparison. So that's the same thing as saying 20 milligrams. Remember, there are 1,000 milligrams in 1 gram. So I could say that that's 2.0 times 10. What should my exponent here be? Is it -2, -3, or -4? If it's 20 divided by 1,000.
Would it be -3?
So, right, 20
Well,
to,
-2, because you put
nice job. So this is where it's really useful to make sense of, right? Sometimes you could write it just as 20 times 10 to the negative 3, right? And if you're inputting that for the purposes of calculation, that would be fine. But if you were writing it as an answer, it would be more appropriate to use the scientific notation of 2.0 times 10 to the negative 2. And that's going to be helpful for us because we need to know the number of sig figs. So we're going to do the same calculation now for our 80, right? So this is an 80 kilogram person. So in this case, it's a similar type of conversion, right? But a different conversion factor. So in 1 kilogram, there are 1,000 grams. And if it's been a minute since you've done metric conversions, this is a nice refresher. Okay, so that's going to be 8.0 times 10 to the, what do you think? 80 times 1,000. So that should be 8 times 10 to the 4th grams, or so notice, as part of this refresher, our negative exponents tell us when something is small. Our positive exponents tell us when something is large, right? In this case, we're converting to the same unit so that we can do a comparison. So what is the comparison that we need to do? Well, we need to determine the grams of lead per gram of body weight. Let me say that again. We need to determine the grams of lead per gram of body weight. So all we're going to do then is take these two numbers and put them in a ratio. So I have 2.0 times 10 to the negative 2 grams, right? That's the dose that leads to poisoning. And then I have 8.0 times 10 to the 4th grams. And so when I do that calculation, the 0.02 divided by 80,000, I get 0. Actually, let's do it this way. I can do 0.25 times 10 to the negative 6th. Or if I was writing this in accurate notation, it would be 2.5 times 10 to the negative 7th. Okay, so what does that mean? Well, this is grams per gram. So if I'm thinking about this, right, a million is 1.0 times 10 to the 6th. So this is equivalent to 0.25 parts per million. So in this case, right, the solute is the lead. And the solution, or the solvent, is the body weight. So you can use parts per million for all sorts of interesting purposes. So in this case, 0.25 ppm is when, right, someone starts to exhibit symptoms of lead poisoning. So it's not the first time that they experience negative impacts, but it's when those symptoms start to show up. So the reason why we think about concentrations like this is because especially heavy metals like lead actually require very little exposure in order to cause harm. In fact, I've posted in our Canvas link an article that reported about the Flint, Michigan crisis. And there's some really interesting data in there about thresholds and how those thresholds change. Notice, right, this is for an 80 kilogram person. But what if it was a 10 kilogram child, right? Or an infant, right? All of a sudden, then the concentrations or the exposure, right? The dose is what makes the poison in that regard. And so this is why being able to calculate parts per million or parts per billion is super important because sometimes you actually need very little. Hexachromium 6 is another example of something that's a common pollutant in water supplies, of which you need very little to cause cancer. Okay, so if we're thinking about this, then I want you to try this problem on your own. So this is seawater. This is actually where we're going next week. But try this problem, and then we'll come back and do it together. We're going to be looking at ocean water and ocean acidification on Thursday. But this is a good example of a problem that takes the information from ppm and then asks you what volume in liters of seawater would contain 1 gram of gold. So take a moment, think about how you would solve that problem. I'm going to give us some time to think, and then I'll walk through the solution.
Is the 3.9
Mm-hmm.
times 10 to the negative 6
Mm-hmm.
in the unit of parts per million, or is it
Correct.
at parts? Okay, so it's like double million.
So a good way to think about that, right? So that means there is 3.9 times 10 to the negative 6 grams per 1 million. So 1,000, comma 0,000 grams of seawater. And I'm going to use the symbol for gold, AU. So there's 3.9 times 10 to the 6th AU per 1 million grams of seawater. Okay, so if, right, we're trying to figure out what the volume in liters would be if it was 1 gram of gold, we're going to think about this ratio. So we have 3.9. Oh, that's a terrible 9. Sorry, let me fix that. So 3.9 times 10 to the negative 6th grams. And that's going to be 1.0 times 10 to the 6 grams, which is the same thing as writing it out in standard form. And I want to know, right, if I have 1 gram of gold, right, how many grams of seawater, right, would I need? Except in this case, they're asking for the volume in liters. So I have to do a little bit of backtracking to be like, okay, I know the density of water is 1 gram per milliliter. So if I know the amount in grams, then I can convert to volume. And from volume in milliliters, I can convert to volume in liters. So let's do that, right? These are very dilute solutions, right? What is this value going to be? So I'm going to replace our question mark with an x because that's the variable that we're solving for. And how do I solve for a problem like this? Well, I cross multiply, so I have 3.9 times 10 to the negative 6th grams. And that's going to be times x. And that's going to be equal to 1 times 10 to the 6th grams times 1 gram. And then in order to solve, I need to get x by itself. So I'm going to divide everything by 3.9 times 10 to the negative 6th. But I have to do that on both sides. And so then x is going to be equal to 3.91 times 10 to the 11th, and that's going to be grams. Obviously, I can convert that to milliliters, right? If I assume 1 gram per 1 milliliter, then it becomes 3.91 times 10 to the 11th milliliters. And then if I wanted to convert that into liters, right, I know that there are 1,000 milliliters, so I divide by 1,000, so that would be 3.91 times 10 to the 8th liters. That is a lot of ocean water for 1 gram of gold. But that's the process that I would use, where if I was given ppm and I had to work backwards to figure out, well, what's the amount in grams, and then how do I use that amount in grams to figure out volume? The reason why I think it's super important to have familiarity and ease or comfort working with ppm or ppb is that increasingly there are any number of chemicals that are exposure is actually very limited, but can still cause significant harm. We're going to look at some examples of those on Thursday, but PFAS is a great example. So these are polyfluorinated compounds that you actually don't need a lot of exposure to in order to cause harm. So that's the reason why we're becoming proficient in calculations in ppm and ppb. Okay, I want to show you, I'm super excited about our pattern of inquiry for this week. So let me stop sharing for a moment and switch to our Canvas page so I can show you our pattern of inquiry. Part of the reason why I'm super excited about this is I made the decision that I was not going to do exams because I had a conversation with a student at the end of last semester where they said, exams stress me out so much. I just wish I could do more practice problems so that I would really feel comfortable solving the problems on exams. So for this summer, I made the decision that I wasn't going to have exam questions, but instead we were really going to push our practice with the pattern of inquiry. And so the goal here is that each question that I'm asking really requires you to engage at a different type of cognitive load. And let's talk a minute just about what I mean by that. So remember, at this point, hopefully you have some type of working definition in your mind of what solubility is. And so the first question really just asks you to think about, well, how do I describe solubility? I've given you a textbook reference answer, right? The dividing line between soluble and insoluble is typically 0.1 molar at 25 degrees Celsius. Any substance that can form 0.1 molar or more concentrated is considered soluble. Any substance that fails to reach that 0.1 molar solubility is defined as insoluble. Now, that doesn't mean that there isn't any of that compound in water. It just means there's a very limited. So sometimes, right, we have compounds that are described as slightly soluble, and that's an important consideration. So I want you to think about how you would describe solubility in your own words, right? If someone were to stop you at the grocery store or on the bus, or right, if you were going for a walk with friends and someone was like, "Hey, I heard this word. What does it mean?" How would you describe it to them? Okay, the next problem that I want you to wrangle are the solubility rules. So I think this is a really interesting space because I know that in general chemistry, students memorized these solubility rules. But at this point, I think that you are in a space where you can see that it's a little bit more nuanced than that. So these rules exist because each of these compounds has a KSP or a solubility value that puts them into the soluble or insoluble category, or potentially slightly soluble. So I want you to think about examples of each of these, of what makes something soluble or what makes it insoluble. And if it's helpful, you can look up KSP values. There's any number of tables that are available, but it's super helpful if you can see an example of each. So both what's an example and what's a non-example, or what's something that's insoluble. And to help you out, I've also given you an insolubility or solubility table. Um, I feel like it's super helpful at this point to recognize that these rules are in order, right? So rule number one trumps rule number two. Um, so that's useful as an information, and it kind of helps with the nuance. But there's a solubility table for your reference. Notice you could pull examples from the solubility table in order to answer number two. Okay, let's talk about the apply. So we did a problem like this with lead fluoride, but I want you to notice that I've changed the temperature and I've changed the mass per volume, or the weight per volume. And this is the really important part. As you increase temperature, you typically, for many compounds, can increase their solubility. And so I want you to do a calculation for KSP and really drive home the this is temperature dependent thinking in your mind. So notice all three of these problems in terms of their structure are, right, taking an idea, making sense of an idea, and then applying an idea. So those are what we call lower levels of Bloom's taxonomy, where those are skills that, right, once you master those, you can do more challenging or more difficult analyses. So here's an example of an analysis. So I gave you data for the Marina Coast Water District. Now, what's interesting to me is that they report in aggregate, right? In part because they are looking overall at the water quality of Marina, and the average can actually hide data. So they collected 539 samples. One of those samples was from a well where the value was 6.30 milligrams per liter. And so I want you to figure out, does this value fall below, at, or above the action level? And so for reference, I gave you a link to the EPA's lead action level, but it's also listed here. So for lead, it's ppb, and the action level is 15. So if it's 15 ppb, right, then it's necessary to take action because that's no longer safe. So you're going to do a calculation and figure out, based on this data, is the water safe? Okay, the next problem that I'm super excited for you to explore is actually the Flint water crisis. And so we've talked about this a little bit, right? It was widespread lead contamination in the city's drinking water. And really what happened was they switched to a new water source. And when they changed to the Flint River, um, the alkalinity, the level of the pH changed. And so that meant then that the lead from the pipes was leaching into the water. And so the data that they had, which you can reference the original paper in our Canvas, reported an incidence of elevated blood lead levels from 2.4% to 4.9% after they changed the water source, right? And there are some neighborhoods that had blood lead levels with a 6.6% increase. So you're going to show these calculations as molarity, or moles per liter, as well as ppm and ppb. And then what I want you to think about is, what is the level of exposure in the water that you think would lead to blood lead levels with that great an increase? So we're going to compare those to the EPA recommended action levels and start to think about, whew, what does that mean? And then, right, the last one is recognizing that it's all about context. So, in a dose response relationship for children aged 1 to 5 years, for every 1 ppb increase in water lead, the blood lead increases 35%. So I listed the original source and the research paper there. So the greatest risk of lead in water may be to infants on reconstituted formula. So when someone makes formula, if they mix it with tap water, there's a risk to that infant. So I'd like for you to create a data table showing the correlation between kind of tap water lead levels and blood lead levels. So you're going to have to use the data from 5. And then I want you to create a claim evidence reasoning statement. Why is there a greater risk of lead level exposure for children and infants? And you can actually use what we did for the body weight calculation as the example in class to help you with this. So think about what's the mass of a child? What's the mass of an infant, right? What's their body weight relative to the amount of lead that they're being exposed to? So I think these problems are a great example of diving deeper based on the types of problems that we've solved together in class today. And lead is just one example. There might be others that you could explore as potential contaminants, either based on the area in which you live or based on maybe a natural disaster. So sometimes one of the challenges that we encounter is you have a stable water source, but then something like flooding occurs. Or in the case more recently, we're going to take a look at the Moss Landing battery fire that occurred and how that contaminated a significant level of heavy metals into the local Elkhorn Slough. And the groundwater that feeds a lot of people. So there are a bunch of examples that we could look at here that are relevant, but I want to show you um, the article in Canvas just so that you have that as a reference as well, because I found this to be a fascinating read, and you're going to have a reading quiz that's actually based on this article next Monday. So let me show you. Okay, so these are the slides from our session today. And remember, I always post the recording from our session together, so you have that available via our YouTube channel. This is our pattern of inquiry. Notice that's due on Monday. I'm in the process of grading the patterns of inquiry you've submitted so far. You're going to get an individual email from me this week, just checking in. But this is the article that I wanted you all to have reference to. So it's a fascinating story, and it's just a really interesting read. But I think this will give you enough context that it will both help with your claim evidence reasoning, and I think some of the data calculations that you need to make. And so just to give you a little bit of context, so Dr. Hannah Atisha and Dr. Champney Schnepp are physicians who were with the Children's Hospital, and they ended up measuring these values and really being taken aback by the concentrations that children's were being exposed to. And so this article kind of describes the process that they used for analyzing that data. It's a fascinating read, and I think a really great example of chemistry and context. The next piece that I want you to think about um, in terms of our course, and I think this is the last one for today, is we're going to start to think about the effect of pH. So we've referenced it a couple of times, but I've given you the pH scale just as a reference point to get started thinking about. On Thursday, we're going to do a deeper dive here, but you can start to think about the relationship between pH and the solubility of compounds. So that's where we're headed next. We're going to take a look at ocean acidification and actually do a deeper dive talking about how the change in pH affects things like carbonate ions, for example. That's the direction where we're headed next. So Thursday is going to be another chemistry and context, thinking about solubility, but in a slightly different context, thinking about the ocean. If you've got any questions, I will happily stay on and answer any questions that you might have. But otherwise, I will see you on Thursday, and I wish you a great rest of your Tuesday.
Have a
Thanks so
nice day.
much. Have a great one. Take care.
Thank you.
Bye.
Bye. Take care. Reese, how you doing?